Welcome back, and welcome to Lecture 10 in this series on Einstein. In this lecture, we're going to explore the single most ambitious scientific endeavor of Einstein's life and career. What I'm talking about here is Einstein's search for what he called a unified field theory. Looking back over these lectures so far, they've all more or less focused on various aspects of two major subjects. The first six were about the development of the theory of both special and general relativity. In those lectures, we also talked a lot about different applications of relativity, including black holes, gravitational waves, and even cosmology. And then in the next three lectures, we talked about quantum theory, including both Einstein's contribution to its development and his struggle to overturn it. By any reasonable measure, relativity and quantum mechanics are the areas in which Einstein made his greatest and most lasting contributions. But these were not the only areas in which Einstein was interested. Throughout much of his life and his career, Einstein's mind was fixated on yet another challenge. For a period of 3 decades, Einstein searched with very little success for a unified field theory. Such a theory, Einstein hoped, would combine and merge the theory of general relativity with the theory of electromagnetism, somehow fusing them together into a singular physical and mathematical framework. The theory that Einstein had hoped to discover would be far more powerful and more far-reaching than either of these individual theories could have been on their own. Unification has played a very important role in the history of physics. In fact, I'd argue that many of the greatest accomplishments in physics are examples of a unification. By unification in this context, I have in mind cases in which there were once 2 or more ideas that were thought to be distinct and unconnected from each other, but then were later shown to in fact be different aspects of the same underlying phenomenon. Consider, for example, what we call gravity. Prior to Isaac Newton, gravity was seen as a force that pulls things downward and toward the Earth. And also independently, it had been shown by Johannes Kepler and others that planets follow elliptical orbits around the Sun. But at the time, no one knew why planets follow these orbits. It was just known that they did. And at the time, there was no reason to think that these things, the falling of objects and the motion of planets, had much or anything to do with each other. But Isaac Newton changed all of that. With his theory of universal gravitation, Newton combined or unified these seemingly very different phenomena with a single overarching principle. His proposal was that all kinds of mass attract one another with a strength that's proportional to their masses and inversely proportional to the square of the distance separating them. With this simple relationship, Newton found an idea that could explain both why massive objects are pulled toward the Earth and why planets, and moons and comets for that matter, follow the trajectories that they do as they move through the solar system. One idea which could be described by one equation could explain a great deal about the universe. Another particularly important example of a unification in physics took place almost 200 years later, in the 19th century. Prior to this, electricity and magnetism were conceived of as unrelated phenomena. Electricity, on the one hand, was responsible for things like lightning and static charge. And on the other hand, magnetism caused compass needles to point north. They were seen as entirely different forces, which acted in different ways and acted on different things. But by the mid-1800s, the work of physicists such as Michael Faraday and James Clerk Maxwell had shown that electricity and magnetism were not unrelated at all. In fact, they discovered that a magnetic field itself is nothing more than a moving or changing electric field. In other words, magnetism is just electricity in motion. Its effects might seem different, but beneath it all, it's really just another aspect of the same underlying thing. Today, physicists talk about electromagnetism as a singular aspect of nature. And from a modern perspective, that's in fact what it is. But before the unifying work by Faraday and Maxwell, the phrase electromagnetism wouldn't have made any sense at all. It would have been saying like sonic algebra or high temperature typing. Only after the unified theory of electromagnetism was discovered could one see any reason to think about electricity and magnetism as being connected to one another in any meaningful way. Sometimes, when two ideas are found to be deeply connected, This reveals new and surprising things in the process. In the case of electromagnetism, the equations that were discovered to relate electricity and magnetism to one another also describe the nature and behavior of light waves. As we've discussed earlier in these lectures, light is an electromagnetic wave, a combination of oscillating electric and magnetic fields, which move together through space. But before the unification of these phenomena, no one had any reason to think that light had anything to do with electricity or magnetism. Every time that physicists manage to successfully unify a set of seemingly unrelated phenomena, they're left with a more powerful theory. By more powerful, I mean that a unified theory can explain more and do it with less. Newton's unified theory of gravity explains why objects fall down and why planets move in elliptical orbits. And it explains all of this more simply than the theories that preceded it could. But in addition, Newton's theory can be used to understand and predict many things that the preceding theories simply couldn't. From Kepler's equations, I can't tell you how heavy a bowling ball will be on the moon, or predict the trajectory of a satellite around the Earth. But I can predict these things using Newton's theory. Because it unifies multiple ideas into one, it can explain more. And that's what I mean when I say that a theory is powerful. Okay, so let's go back to Einstein. Einstein's quest for a unified field theory started only a couple of years after he completed his general theory of relativity, in or around 1918 or so. At the time, there were two fundamental theories that were central to how physicists understood their universe. One of these theories was Einstein's new general theory of relativity, which explained the phenomenon of gravity and its relationship to space and time. And then there was the theory of electromagnetism, usually written as a set of four equations known as Maxwell's equations. Maxwell's equations can be used to describe a wide range of phenomena associated with electricity and magnetism, including that of light. So from Einstein's perspective, here were two different facets of nature. Both of these theories were individually quite powerful and quite mathematically elegant. Einstein admired James Clerk Maxwell a great deal, and he held Maxwell's equations of electromagnetism in very high regard. And Einstein also, of course, was quite fond of his own theory of general relativity. These two theories were among the greatest accomplishments in all of physics. As far as anyone could tell, the theories of general relativity and electromagnetism seemed to be basically unrelated to one another. But Einstein wasn't so sure that this was really the case. After all, electricity and magnetism seemed to be unrelated until Faraday and Maxwell showed us otherwise. Einstein wanted to do something similar with general relativity and electromagnetism. Like many of the greatest physicists before him, Einstein wanted to make a more powerful and widely applicable theory that could predict and explain more than its predecessors could. The first attempt that I am aware of to build a unified field theory wasn't made directly by Einstein himself. Instead, it was by the German physicist and mathematician Hermann Weyl. That being said, Einstein and Weyl were in communication during this time, and they discussed some of the aspects of this problem together, so at least to some extent Einstein was involved. From Weyl's perspective, there was really one central challenge that made it so hard to combine general relativity and electromagnetism into a single unified field theory. This challenge basically boiled down to the fact that general relativity is a theory of geometry, while electromagnetism is not. Maxwell's equations describe the forces that act on electrically charged particles, but they don't involve any changes to the geometry of space or of time. Weyl felt that if he wanted to merge these two theories together into a common framework, he would need to find a new and more geometrical way to think about and formulate the theory of electromagnetism. In general relativity, the geometry of space and time is described by a mathematical object called the metric tensor. You might remember that we talked about tensors way back in lecture 2. A tensor is basically a special kind of matrix or array of numbers. In general relativity, the metric tensor is a 4x4 array of numbers, so it contains a total of 16 entries. But it turns out that of these 16 quantities, 6 of them are redundant with the others, so there are really only 10 independent numbers described by the metric tensor. And it turns out that you need all 10 of these numbers just to describe the effects of gravity. In other words, if you knew the values of all 10 of these numbers at every point in space, you could perfectly describe the geometry of the universe. and that means that you could perfectly describe the effects of gravity and how it affects the motion of objects. The problem with combining general relativity with electromagnetism is that you need all 10 of these quantities to describe the effects of gravity. And if you wanted to incorporate electromagnetism, you would need at least 4 more numbers at every point in space. This made it hard to see how you could explain both gravity and electromagnetism in terms of geometry. There just aren't enough numbers in the metric tensor to describe both gravity and electromagnetism at the same time. There just didn't seem to be room for electromagnetism in the math. To try to get around this problem, Weil proposed a version of non-Euclidean geometry that he thought was even more general than the system of geometry that Einstein had based general relativity on. In doing so, he argued that it was possible to construct a geometrical system that wasn't limited to the 10 independent numbers that were contained within the metric tensor proposed by Einstein. In addition to those 10 numbers, Weil's version of the metric tensor contained other additional quantities. And Weil hoped that these additional numbers could somehow encode the effects of electromagnetism. The theory that Weil ultimately came up with was very complicated, although it seems to have been mathematically sound. But physically speaking, it just didn't make much sense. After a series of exchanges with Einstein, even Weil became convinced that his work hadn't gotten them any closer to a viable unified field theory. But although Weil abandoned his efforts in this direction, he had been a trailblazer, and many others would pursue similar paths over the years to come. Only a year or so later, another idea in this direction was proposed, this time by a mathematician named Theodor Kaluza. Most people find Kaluza's idea to be pretty strange and surprising. What he proposed was a unified field theory in which the space and time of our universe isn't 4-dimensional, but that instead consists of 5 dimensions. To see why a 5th dimension might be helpful in building a unified field theory, think again about the metric tensor. I told you a few minutes ago that this tensor is a 4x4 array of numbers, for a total of 16 entries, 10 of which are independent of each other. Well, this tensor is a 4x4 array of numbers because it was formulated in 4-dimensional spacetime. But if spacetime is 5-dimensional, then instead of being a 4x4 array, the metric tensor will be a 5x5 array of numbers, for a total of 25 entries. After removing all of the redundant entries, the 5-dimensional metric tensor contains 15 independent quantities. 10 of these 15 numbers are needed to describe gravity, and this leaves us with 5 others, which is more than enough to potentially encode the phenomena of electromagnetism. There is, of course, one immediate and obvious objection that one might raise to Kaluza's 5-dimensional theory. As far as we can tell, our universe doesn't have a 5th dimension. If there really is an extra dimension of space, there better be a good reason for why we don't notice it. Fortunately, there is a way that a 5th dimension might be able to remain hidden in a system like Kaluza's. In this geometrical system, the 5th dimension isn't like the others. The 3 dimensions of space that we're familiar with are large, and as far as we know, they go on forever in any given direction. If there were an extra dimension like this, it would be impossible for us to not notice it. But the 5th dimension being imagined by Kaluza doesn't go on forever. Instead, it's wrapped up or curled up into a tiny little circle. By this, I mean that if something moves even a short distance along the direction of the 5th dimension, it would simply return to where it started. Moving in this direction would be like walking around the circumference of a tiny sphere. If the circumference of the 5th dimension is small enough, it would be almost impossible for us to perceive it. In most respects, it would seem just like we were living in a universe with only 4 dimensions of space and time. It was in 1919 that Kaluza described his idea to Einstein for the first time. And despite the fact that there were significant problems with the 5-dimensional theory, Einstein seems to have liked it a great deal. With Einstein's help, Kaluza managed to publish his theory a couple of years later, in 1921. And only a few weeks after that, Einstein himself wrote and published an article that investigated some of the aspects of similar 5-dimensional unified field theories. But despite this enthusiasm, it was pretty clear to Einstein and to others that there were serious problems with Kaluza's theory. Einstein continued to work on this theory not because he thought it was a viable unified field theory, but because he thought it might lead to something more promising. After all, while Einstein was developing general relativity, he went through several incorrect versions of the gravitational field equations before he found the right answer. Sometimes scrutinizing a wrong answer can help you to find the right one. Another scientist who worked on unified field theories during this period of time was the famous astronomer and physicist Arthur Eddington. In some ways, the proposal that Eddington came up with was similar to the ideas pursued earlier by Weil and Kaluza. But in other ways, it was really very different. For one thing, Eddington didn't focus on expanding the metric tensor. In fact, he didn't focus on the metric tensor at all. Instead, he focused on a different mathematical structure known as the affine connection. In the end, Eddington didn't really get any closer than Weil or Kaluza to building a viable unified field theory. But Eddington's work was important because his approach was quite different. And along with Kaluza, Eddington probably had the most influence on Einstein's later efforts to develop such a theory. And furthermore, Eddington did a lot to emphasize just how much predictive power a unified field theory might be able to offer. For example, he imagined that such a theory would be able to explain things like why the electron and proton have the masses that they do. From this perspective, it's not hard to see why the idea of a unified field theory was so alluring to both Eddington and to Einstein. Einstein himself began to focus on unified field theories in the early 1920s. During this period of time, he remained enthusiastic about the work that had been earlier done by Kaluza and Eddington. In fact, a lot of Einstein's early work in this area consisted of extending and building upon these earlier ideas. In many ways, Einstein took the work of Eddington and Kaluza as starting points for his own search for a unified field theory. Einstein was deeply enthusiastic about this program of exploration. But in this respect, he was relatively isolated, and most physicists didn't share his excitement. Quantum physics was developing rapidly, and that seemed to be occupying the bulk of the field's attention during this time. But as we discussed over the past few lectures, Einstein was deeply unhappy with the developments occurring in quantum theory, and he became only more opposed to it as quantum mechanics continued to develop. Einstein's views about quantum mechanics also served to bolster his interest in unified field theories. In addition to unifying general relativity with electromagnetism, Einstein hoped that a unified field theory might also somehow be able to restore determinism and scientific realism to the quantum world. In 1923, for example, Einstein published a series of papers that built upon and expanded on Eddington's work. And later in the same year, he wrote another paper in which he argued that this theory might make it possible to restore determinism to quantum physics. These papers of Einstein's were covered enthusiastically by the press. After all, Einstein was already very famous by this point in time. He was the only living scientist that was really a household name. And although few journalists really understood the theory that Einstein was putting forth, they did understand that Einstein was proposing something that was potentially very important. That is, it would be really important if it were true. But unfortunately, it was not true. Few of Einstein's colleagues were impressed by this work. And within only a couple of years, even Einstein accepted that his approach was deeply flawed. If Einstein was going to find a viable unified field theory, he would have to find another way of approaching the problem. Einstein's next major effort in this direction came in the late 1920s, including a paper that he published in 1929. This new approach was based on an idea known as distant parallelism. This approach was very mathematically complex, and to be honest, I've never really been able to understand how the different elements of the theory fit together. From what I do understand, Einstein treated both the metric tensor and the affine connection as fundamental quantities in this approach, trying to take full advantage of both. Once again, the press responded enthusiastically. But again, Einstein's colleagues did not. One of the reasons for this had to do with the fact that Einstein was trying to build a theory that would unify general relativity with Maxwell's theory of electromagnetism. But over the course of the 1920s, Maxwell's classical theory had been replaced by the new quantum theory. Although Maxwell's equations are still useful today, they're really only an approximation to the true quantum nature of the universe. For this reason, many physicists saw Einstein's efforts to unify classical electromagnetism with general relativity as old-fashioned, and it didn't even try to take into account everything that had been learned about the quantum mechanical nature of the universe. Einstein seems to have been hoping that quantum mechanics was just a fad, but about that he was dead wrong. Quantum mechanics was here to stay, and to be viable, a unified field theory would have to deal with that fact. In the years that followed, Einstein continued to explore different approaches in his search for a unified field theory. He worked extensively with five-dimensional theories throughout much of the 1930s and moved on to a number of other ideas during the 1940s and 50s. But none of these approaches ever even attempted to incorporate quantum mechanics. At a time in which most physicists accepted the quantum nature of our universe, Einstein was still searching for a classical unified field theory. In his 30-year search for a unified field theory, Einstein never found anything that could reasonably be called a success. Over these 3 decades, Einstein's fixation on classical field theories and his rejection of quantum mechanics increasingly isolated him from the larger physics community. Furthermore, his work became increasingly mathematical and formal as time went on. There were fewer and fewer thought experiments, and Einstein's physical intuition, which was once so famous, seemed to have been pushed aside and replaced by endless pages of complicated interplaying equations. Even during the last days of his life, Einstein continued to search for a unified field theory, but nothing of consequence ever came of it. When Einstein died in 1955, he was really no closer to a unified field theory than he was 30 years before. In recent decades, physicists once again have become interested in theories that could potentially combine and unify multiple facets of nature. In spirit, these modern theories have a lot in common with Einstein's dream of unified field theory. But in other ways, they are really very different. For one thing, many important discoveries have been made since Einstein's death, and these discoveries have significantly changed how physicists view the prospect of building a unified field theory. In particular, whereas Einstein was focused on electromagnetism and gravity, physicists have since discovered 2 new forces that exist in nature as well, the weak and strong nuclear forces. The strong nuclear force is a force that holds protons and neutrons together within the nuclei of atoms. And the weak nuclear force is responsible for certain radioactive decays and for the process of nuclear fission. It turns out that electromagnetism has a lot in common with these strong and weak nuclear forces. And it's not particularly hard, at least in principle, to construct theories in which these 3 phenomena are unified into a single framework. Such theories are known as grand unified theories, or GUTS for short. And since they were first studied in the 1970s, a number of different grand unified theories have been proposed. Grand unified theories are incredibly powerful, and in principle they can predict and explain a huge range of phenomena. But they are also very hard to test and explore experimentally. It's not that these theories are untestable in principle. If you could build a big enough particle accelerator, you could almost certainly find out exactly how these 3 forces fit together into a single unified field theory. But with the kinds of experiments that we currently know how to build and the kinds of experiments that we can afford to build, it's just not possible to directly test most grand unified theories. There are, however, possible exceptions to this. One is that most of these theories predict that protons should occasionally decay. And this is the kind of phenomena we can look for and build experiments to test. In most of the grand unified theories that have been proposed, the half-life of the proton falls somewhere in the range of roughly 10 to the 31 to 10 to the 36 years. Given that the age of the universe is only a little over 10 to the 10 years, you might think that no protons have decayed yet. But this isn't the right way to think about it. Consider, for an example, an Olympic-sized swimming pool filled with ordinary water. That much water contains roughly 10 to the 33 protons. So if you were to build an experiment that could observe and monitor that collection of protons for an entire year, you could test proton half-lives up to about 10 to the 33 years or so, which is near the middle of the range predicted by most grand unified theories. The most sensitive tests of proton decay that have been conducted so far were made using an experiment called Super Kamiokande, or Super K for short. Super K is essentially a giant tank filled with 50,000 tons of water, surrounded on all sides by sensitive detectors. Because this experiment is so big and because it has been collecting data for so many years, Super K is extremely sensitive to proton decay. But still, they have not found any evidence that the proton is unstable. But they have been able to show that the half-life of the proton must be longer than about 10 to the 34 years or so. In the coming years and decades, even bigger experiments are planned, and these are expected to be even more sensitive to proton decay. Personally, I wouldn't be at all surprised if these experiments discovered the first evidence for proton decay. And if they do, that discovery would constitute the first concrete evidence that the electromagnetic strong and weak forces each fit together into a larger and more powerful grand unified theory. But even grand unified theories are not as far-reaching as the kinds of unified field theories that Einstein spent so much of his life and career searching for. Grand unified theories bring together electromagnetism with the strong and weak forces. They don't connect these phenomena with general relativity. But much like Einstein, modern physicists are also looking for theories that can combine general relativity with the other forces of nature. We hope that such a theory could unify all four of the known forces, including gravity. And since the aim of such a theory is to describe all of the laws of physics that describe our universe, we call a theory of this kind a theory of everything. Einstein spent 30 years of his life unsuccessfully trying to unify general relativity with electromagnetism. Similarly, modern physicists have struggled for decades to understand how general relativity might be self-consistently combined with the other forces of nature. The challenges faced by Einstein were very different from those faced by physicists today, however. Modern theories of everything are fundamentally quantum entities, whereas Einstein's efforts in this direction were entirely classical in nature and generally ignored the role of quantum mechanics. The focus today is on how to merge the geometric effects of general relativity with the quantum mechanical nature of our world. What we're really searching for is a quantum theory of gravity. The most promising theories of quantum gravity explored so far have been found within the context of string theory. In string theory, fundamental objects are not point-like particles, but instead are extended objects, including one-dimensional strings. Research into string theory has revealed a number of strange things about these theories. For example, it was discovered in the 1980s that string theories are only mathematically consistent if the universe contains extra spatial dimensions. Extra dimensions that are similar in many respects to those originally proposed by Theodore Kaluza. Although string theory remains a major area of research in modern physics, there's still much that we don't understand about it. And we don't know for sure whether it will ever lead to a viable theory of everything. I sometimes wonder what Einstein would think about our modern investigations into grand unified theories and theories of everything. In many ways, these modern theories have very little in common with those explored by Einstein during his lifetime. But in spirit, they're really trying to answer the same kinds of questions. At their foundations, they're each trying to explain as much about our world as possible, as simply as they possibly can.